Thank you so much. It's a pleasure to be here and to have been invited. And I'm very sorry about my technical issues yesterday. There was no power anywhere that was nearby, but I'm very happy to be here again. So I want to speak about some work on transcendence, really, related to period integrals of algebraic varieties. Everything I say is going to be joined with Ben Bakker. And though it's a very sort of number theoretic subject, it turns out to have a lot of interaction with the functional world, and in particular, the methods very strongly rely on the O-minimal framework that's been talked about so much, and in particular, the work of Peter Zill and Starchenko. So let me begin by saying an outline of what I want to talk about, which is essentially some transcendence questions and the Grothendieck period conjecture, which is something that's in the classical case extremely number theoretic and extremely open. So what I want to do is I want to motivate what I actually want to talk about by describing the classical setup, and then describe Andre's generalization of it. And then we move to the functional setup. The more geometric case, one can prove a lot more. And essentially, the goal of the talk is to formulate and state the geometric generalization of this period conjecture and explain how it's related to the Ax-Schanuel conjecture, which is a much more familiar statement in sort of this setup, and from which draws from these methods very heavily. So to begin to talk about transcendence, let me start with the classical Schanuel conjecture, which is really about the exponential function. That pretty much says the exponential function is as transcendental as it can possibly be. So the only algebraic relation is that e to the x plus y is e to the x times e to the y. And the formal way to say that is if you have n complex numbers, alpha 1 through alpha n, and they're q linearly independent, then if you adjoin all the alpha i's and you adjoin all their exponentials, the transcendence degree you get just over q is at least n. So it's easy to see that you can make it n just by making all the alpha i's algebraic, or by making all the e to the alpha i's algebraic. But the idea is you can't control both a number and its exponential at once. So this is a very open conjecture, and again, I have nothing new to say about it. There are some known cases. Famously, there's the Lindemann-Weierstrass theorem that if your n numbers themselves are actually algebraic, alpha 1 through alpha n, then their exponentials are transcendental and in fact algebraically independent from each other. So this transcendence degree here is exactly n.
So that should say linearly independent.
I'm sorry, can you say that again, please?
That in the Lindemann-Weierstrass statement, that should say linearly independent.
Oh yes, of course. Thank you. Linearly independent. I appreciate that. That's a great segue, actually. Thank you. Because if they are dependent, if alpha 1 is twice alpha 2, then the point is that an additive q-linear relation between the numbers leads to a multiplicative algebraic relation between the exponentials. So this 2 is also a typo. E to the alpha 1 becomes e to the alpha 2 squared. So essentially, if an alpha is in the q-linear span of the previous guys, then neither it nor its exponential adds anything to your transcendence degree. And that's why you need the q-linear independence. And a fun case I like to always say, because it's a very open question and it's very stunning, that if this was true, it would in particular imply that e and pi, which are known to be transcendental by themselves, are algebraically independent from each other. And the way you get that is you plug in alpha y. Alpha 1 is pi I, and that gives you pi, and its exponential is -1, so that doesn't help you at all with transcendence. And you plug in alpha 2 equals 1, and its exponential gives you e. So you get the transcendence degree of these four numbers is at least 2, but 1 and -1 aren't helping. pi I is the same as pi as far as transcendence degree goes, and so you conclude that pi and E are algebraically independent. So even the case of n equals 2 would imply this wonderful result, which is very open. Okay, so that's the classical case of Schanuel's conjecture. So then one can go in a more general, but as I'll explain, not entirely more general direction, by saying, well, look, pi I is the integral of dx over x. So just consider integral of more general forms, more general integrals. So I'll say this setup quite generally, but you can imagine K is the field of rational numbers for now, or the field of algebraic numbers. And you consider a variety over it. For now, let's think about a smooth projective variety. So X could be like an elliptic curve or any other curve or a higher dimensional thing. Let's take omega to be a holomorphic, or by Gaga, the same thing, algebraic K form on X. And let's take gamma to be a homology class of the complex points of X. Then what you can do, full of typos, I apologize. What you can do is you can integrate omega over gamma. And an example of this is if you have your elliptic curve and you have a 1 form on your elliptic curve, then you can look at the first homology group of E and pick a basis for it, alpha and beta. And then if you uniformize E over the complex numbers, then you can write it as the complex numbers modulo spanned by 1 and Z, some point in the upper half plane. Your two homology basis elements become generated by the class of 1 here and the class of Z. So just the straight line from 0 to 1 and 0 to Z, a line segment, which descends to a loop on E. Omega is some constant times dz. It's hard to say which one, but you get this fun relation that if you integrate omega over beta and alpha and take the ratio, you recover Z, which is the inverse of the J function, essentially, on the J invariant of E. The inverse of this is the usual holomorphic J function, and this is the algebraic J invariant of E. This is like an elliptic curve or a Shimura analog of the log function, basically. So periods give you all sorts of interesting things like this. Now, the above setup is very clean because it's fun to work in smooth projective scenarios, just think about forms. But unfortunately, it doesn't include numbers like 2 pi I or log 2, at least not obviously, because even though 2 pi I and log 2 are period integrals here, they're integrals of the form dz over z over the unit circle or from 1 to 2. This one's not allowed because dz over z is defined on GM, so C star, so it's not projective, it's not compact. And this one's not allowed because we have boundary points, 1 and 2, so it's not a loop. And we want to include all of these things. And so to fix this, we can do a few things. First, we can allow X to be non-projective. We can just think about varieties that are smooth but not projective. Instead of K forms, it's actually more convenient to think about algebraic de Rham cohomology classes. I won't spend much time on this. There's some algebraic definition. Essentially, all of these things you can think of as allowing not just algebraic differentials, but also some meromorphic differentials. So there's some theory here, but it's not very relevant to what I want to talk about. So I'm going to gloss over this point. And to fix this point here, where you have boundary points, instead of cohomology groups, you can allow yourself to talk about relative cohomology groups. So instead of just looking at the homology of X, what you can do is pick a subvariety Z of X and look at the relative homology of X with respect to Z, which basically means you want cycles whose boundary lies entirely in Z. So the simplest case, if we let Z be just the 2 points 1 and 2, and X is GM, then we can allow this integral because we now have the class which goes from 1 to 2. Okay, so then informally, I'll say something more formal in a bit. But informally, the Grothendieck period conjecture says that the transcendence degree of periods is exactly what's required from geometry. So there are some relations just given by the presence of maps between varieties, or things like Stokes' theorem, which enforce certain linear algebraic relations. And the conjecture is that besides that, there's nothing else. Everything that could in principle be transcendental is transcendental. Yeah, so here I'm just pointing out that even though this space in general is bigger than the space of just algebraic K-forms, you can still think about meromorphic differentials, so it's a very similar picture. Okay, so let me say a little bit more about the story of what geometry requires to be true. And there's a few ways to say this. I think that the easiest way to say this is with the notion of this period ring. And this KZ stands for Kontsevich-Zagier. And this formalism I'm taking here is essentially what they had, but it was written down by Ayub first, as far as I know. And what it says is the following. So this is going to be a ring, and it's going to be generated as a K vector space. Remember, K is the field we fixed at the beginning, by just these formal symbols. So we're going to keep track of X and Z for this relative homology group, this base on which we work on. We're going to keep track of K, the dimension we're working in. We're going to keep track of our differential, and we're going to keep track of our cycle. And now we're going to enforce certain natural relations. And they are the following. So first we want linearity. So if we integrate omega over gamma, that should be linear in omega and linear in gamma. So K linear in omega and Q linear in gamma. So require those things. There's the base change one, that if you pull back a differential and integrate it, it's the same as pushing forward the cycle and integrating it. So that's what's happening here. If you get a map, you can integrate the pullback of a differential over gamma, or you can integrate your differential over the push forward of gamma. So you want to insist on this relation. And then there's Stokes' theorem, which basically says that the integral of D of some form over a cycle is the same as the integral over that form on the boundary of that cycle. This is a slightly more complicated version of it for relative homology, but it really is just Stokes' theorem. Okay, so essentially look at the free vector space generated by these symbols and by this relation, by these relations. And it's easy to write this down, but it's actually quite hard to figure out what this is, because you got to figure out what all your possible maps are, and there's lots of possible maps. Oops, sorry. And then there's a natural map from this period ring to the complex numbers, where you just send this formal symbol to the integral of omega over gamma. Okay, so then the Grothendieck period conjecture, which wants to tell about the transcendence of these periods, says the following slightly more complicated thing, and this looks unnaturally complicated, but as we'll see, you can think about it in a slightly easier way. It doesn't quite say this is injective. It says that this map makes EV a generic point of the corresponding scheme. So an easier way of saying it, maybe, or a more algebraic way of saying it, is the kernel of this map is a minimal prime ideal. And that's sort of an algebraic way. What it amounts to is an algebraic way of saying that no transcendence degree is lost by going from this period ring to its image. This is for K, by the way, in Q bar. Obviously, if K is not in Q bar, if K is some arbitrary complex number, if some arbitrary subfield of the complex numbers, then you can have coincidences that aren't predicted by geometry, because you can just add whatever periods you get to your field K. You can, of course, ask for more. You can ask for this map to be entirely injective, and that is the Kontsevich-Zagier conjecture. And it turns out, as shown by Ayub, that this Kontsevich-Zagier conjecture is almost equivalent to the Grothendieck period conjecture. It's that, together with the statement that this formal period ring is a domain. Okay, so that's kind of the number theory framework for studying transcendence degrees of periods. Everything is very open. There's a way to rephrase this in terms of motives and group theory, which is more complicated, unfortunately, if you're thinking about number theory. But when we go to the geometric framework, it'll be less complicated. So let me say a little bit about it very quickly. This was written down by Kontsevich, and Nori wrote a lot about this in informal lecture notes. I guess they weren't actually informal; they were never published. So just some sort of Tanakian formalism that I will say nothing about gives you a pro-algebraic group, which I'll call the motivic-Galois group, such that essentially the spectrum of this group is the period ring we just defined. Whoop. And then it's more natural to think about motives where essentially you have objects like these nth cohomology groups of X relative to Z, and then you complete it in some way that, again, I don't want to talk much about, but essentially you allow maps that come from geometry and you allow kernels and co-kernels and stuff like that. And then given a motive, so for example, some formal object like this, there's a Q vector space, which I'm going to call M singular, which in our case is just the literal singular cohomology, the relative cohomology. And there's a map from the motivic-Galois group that acts on this cohomology. And this allows us to talk about the motivic-Galois group of a single motive, not just the abstract one. The heuristic here is that given one of these cohomology groups, this motivic-Galois group image is just going to be everything which respects the constraints coming from geometry. So then it's even though this definition is kind of complicated and unfamiliar, perhaps, you can state the Grothendieck period conjecture very cleanly here, which is that if you have one of these motives, which again, for simplicity, you can think of as just a cohomology group, then if you adjoin all of its periods, all these integrals of all these omegas over gammas, the transcendence degree is the same as the dimension of the corresponding motivic-Galois group. Okay, so one example that's very abstract. One kind of nice example is if you think of M as the motive of GM, where GM is X, relative to the pair of points 1 and Q, where 1 and Q are your Z. This is defined over whatever field little q is defined over. So then the periods you get are just you integrate dx over x over the loop around 0. That gives you 2 pi I. And then you can integrate them from 1 to q, and that gives you log q. And this q is here because this case you're defined over q adjoint little q. And then what this tells you is that your transcendence degree is at least 1 when q is torsion, when it's a root of unity, because it turns out the motivic-Galois group in that case is just GM. And 2 if q is non-torsion, because the motivic-Galois group in that case is GM semi-direct GA. It's the upper triangulars with 1 at the bottom right. Upper triangular 2 by 2 matrices with 1 at the bottom right. So you can compute these quite straightforwardly, at least in the case of one motives, that's due to Andre. So you get this very concrete statement, and you can also make a statement for an elliptic curve, take an elliptic curve over Q. Then if you adjoin its J invariant, and you also adjoin all 4 period integrals here. Now there's only one holomorphic form over E, but there's another theorem cohomology class in the H1, so that's why there's omega 1 and omega 2 here. And you adjoin these 4 numbers. Well, you get something independent, degree 4 if E is non-CM, and degree 2 if E is CM, because you have additional symmetries. So this is just here to show you that you get very concrete conjectures from the Grothendieck period conjecture, even though the statement is kind of abstract. Okay, now one defect of the Grothendieck period conjecture, or maybe not a defect, but one thing you might want that you don't get, is the Grothendieck period conjecture does not, strictly speaking, generalize Ax-Schanuel's conjecture. And the idea is that even though log is a period, the exponential function is not a period. So you can't prove anything, of course, but in fact, conjecturally, E itself is not even supposed to be a period. You shouldn't be able to integrate algebraic forms over Q, over cycles, do some algebraic manipulations and get E. So how do you deal with this issue? Well, the idea is that even though E is not a period, you can still think about it in terms of periods. In fact, how is E defined? E is defined to be the number such that log of E is 1. And log of x is a period function. It's the integral of dx over x from 1 to x. dt over t from 1 to x. Sorry, bad habit. And so given this way of thinking about E, how can you incorporate that into the period conjecture? Well, Andre had a very nice idea, which is, look, let's not limit ourselves to subfields of the algebraic numbers. Let's allow arbitrary subfields over the complex numbers. But of course, as I said before, if you allow arbitrary subfields in forms of arbitrary coefficients, anything can be a period, and you can't expect things to be transcendental without inputting some sort of condition. And so the idea is, okay, we can allow K to be transcendental, but we're going to pay a price the more transcendental we make K. So that equality becomes an inequality now. And it says, if we take M to be a motive over K, so for example, just think about it as some algebraic variety over K, where K might involve some transcendental numbers. Then if I adjoin all the periods of M and I adjoin K itself, the overall transcendence degree is at least the dimension of this motivic Galois group, this sort of algebraic geometric symmetry group. And now it's really an inequality, and this should remind you of Ax-Schanuel's conjecture, which also has an inequality now. So to deduce Ax-Schanuel's conjecture from this generalized version due to Andre, you do the following. You let X be GM and Z be 1 together with e to the power of, this is also a typo, alpha 1 through alpha n. And then there's other de Rham cohomology classes, but the only interesting one is this form dz over z. And if you integrate that from 1 to each of these e to the alpha aj's, e to the alpha j's, you get the alpha j back. Now you can compute this motivic Galois group in this case, and you get m plus 1. So if you adjoin 2 pi I and all of these alpha i's, which is the periods in this case, and you adjoin the field K, and to adjoin these, to talk about these points, K has to include all these e to the alpha i's. The transcendence degree is at least m plus 1. And so if we remove a number from here, it can drop by at most 1. And so we recover Ax-Schanuel's conjecture. So again, the idea here is very interesting from the perspective of the Andre-Grothendieck period conjecture. The way to think about Ax-Schanuel is the more fundamental objects are these exponentials, and these alphas are the periods you get. And if you adjoin the whole thing, then either from here or from here, you get transcendence degree m. So that's the Andre-Grothendieck period conjecture in the number theory setup. Okay, and now I want to talk about the geometric setup, which is perhaps surprisingly, perhaps not, actually ends up being a lot more familiar in many ways. So to talk about this, we have to replace the base field Q with some other field. And we have to replace the target of our evaluation map EV. Right? So if you think about it, what we're doing in the number theory setup, we were doing all our algebraic geometry over Q. All of our varieties were defined over Q. But all of our integrals were defined over the complex numbers. The complex numbers is sort of the big field we allow ourselves to talk about in order to get all of these periods. So now we're going to replace Q with some function field over the complex numbers. So some finitely generated field over C. And we can think of this K as the function field of a complex algebraic variety in many different ways, actually. And our C will be replaced with a much bigger field K hat, which there's many choices for what this K hat can be. A very convenient one is germs of meromorphic functions at a point. And in fact, this is a minor point where we deviate slightly from classical work of Ayub and Nori, because in order to allow C to be this, germs of functions at a point, the problem is if you pick a classical point, like if you take germs at an actual complex point, then there are some open sets which don't include that point. And then it becomes kind of hard to talk about that. And so instead we use an infinitesimal point, which you can think of in or minimal setups. But essentially what we do is we take a small arc in a complex variety, like an infinitesimal arc, and we look at germs of that arc to make sure it's present in all models of this complex algebraic variety. But okay, I mean, that's a technical point, doesn't matter so much. You can think of k hat just as germs of meromorphic functions. So then varieties over k become varieties over x for some model x of k. Like a variety over k, you can think of as just a family of varieties over some model x of k. And then what do these periods become? Well, you have algebraic differential forms on this model over x. They have fiberwise periods, and that gives you functions downstairs on x. And so studying periods over k is the same as studying periods as meromorphic functions on your base x for some model x. Now, there's some complexity coming from the fact that if you change which period you want to study, you have to change which model x you look at. Essentially, you have to shrink the open set more and more. Nonetheless, periods give you these very convenient ways to think about things. In particular, the function log x is just a period now over GM, which corresponds to the field C adjoin x. Because we're just integrating dy over y from 1 to x. Okay, so let's talk about periods and how they vary in families. So suppose you have a base x, an algebraic variety, and a smooth projective family over x, which we refer to as the map f from y to x. So we can take a flat homology cycle gamma, which just means in every fiber of this map, you take a homology cycle, like a little loop or a simplex or something, and you move it around in this family in a locally constant way. And you take an algebraic form, so you take a form in every fiber that varies algebraically over the base. And then given a point downstairs, you can consider the function which takes that point to the integral of the corresponding form over this cycle, gamma sub x. And then what you can do, if you consider the germ at this arc point I described, is you can consider the field where you take k and you adjoin all of these integrals. That'll be some subfield of the field of all meromorphic functions. And again, this is a minor point, but given any motive, you can do the same thing and get the periods of this motive. And then you can ask about the transcendence degree of all of these functions. Okay, so it turns out that you still have these motivic Galois groups like before by the same formalism. And for this is, again, I'm going to gloss past this point, but for those who are interested, in this case, what we want to do is not talk about the motivic Galois group of K, but the relative motivic Galois group over C, which is the kernel of a map like this from K to C. Essentially, what this is saying is we care about the variation of these functions, like as functions on the base, but we don't care right now in the functional case about transcendence of actual complex numbers. Actual complex numbers aren't interesting to us. We're going to only think about transcendence over C as a sort of constant field. And that's why we're going to take this kernel instead of this entire group, which would record that extra information. And then for any motive, again, you can look at the relative motivic Galois group of it, which is the image not of this whole big group, but of this smaller one. Okay, so these motivic Galois groups are very unfamiliar objects, I assume to most people. However, in the function field case, they have a very nice description, which allows you to forget about them, which is that this relative motivic Galois group is just the algebraic monodromy group of M. So in other words, you have your motive, think about it as this family Y over X. Then these fibers become these relative cohomology groups. So for example, think of a family of elliptic curves. For every fiber on the base, you have your two cycles. And then as you go around in a loop on the base, you continue these cycles and you get some monodromy action. And then it's a risky closure, just in GL is going to be some algebraic group. And it turns out these two are exactly the same. So this was written up by Ayub. It was also proven by Nori, but again, in unpublished notes. And so in this case, it's exactly the same. So these symmetries imposed by geometry, you can detect just from the underlying topology of the base. So that makes this analysis possible, because otherwise talking about motivic Galois groups is very difficult. Okay. So there's also a theorem due to Ayub, and again unpublished due to Nori, which says that essentially the Grothendieck period conjecture is true in this setup, that the transcendence degree of all the periods, if you adjoin them all, can literally be read off from the dimension of the monodromy of the relative motivic Galois group. And essentially what this amounts to, well, I shouldn't say that because there's a lot of complications for motives, but one big input in what comes up here is the Picard-Fuchs equations and some differential Galois theory. Essentially, you want to understand the differential equation from the action of monodromy that you get. And that's one big input that they have. And then there's a lot of sort of formalism with motives to make sure this all works. But that's where this comes from. That's sort of known. And what I want to describe is that in this setup, it turns out you can just actually formulate and prove Andre's generalization of the Grothendieck period conjecture. So if instead of working with motives over K, we allow for any intermediate subfield L between K and this bigger field K hat of germs, and we allow for motives over L, we have this exact same inequality, that if you adjoin L together with all of these periods, you look at the transcendence degree over K, then at the very least, you get the dimension of the motivic Galois group here. And just like in the classical case, you can't expect equality here, again, for the same reason that in the Ax-Schanuel's conjecture, you can't expect equality. If you adjoin n random numbers and their exponentials, they're probably all algebraically independent, and you will get transcendence degree 2n instead of n. It's the same thing here. Essentially, this setup is a trick to allow you to sort of think about conspiracies, and in that way talk about like inverses of period functions and constructions like that. Okay, so this is the theorem I want to talk about. Sorry, I'm just trying to, for some reason my clock isn't showing, so I'm just trying to figure out the time.
15 minutes.
Left?
Yeah, 15 minutes left.
Perfect, thank you very much.
You're welcome.
All right. Okay, so now let me, in the rest of the talk, I want to explain the proof, I guess, but instead of talking about the proof, because really the proof here isn't at this point that interesting. It follows from known techniques with some mild tweaks. What I want to explain is how, in fact, the Andre-Grothendieck period conjecture in the function field case essentially ends up being equivalent to a version of the Ax-Schanuel conjecture for periods. It's just a natural generalization of Ax-Schanuel, which gives it to you. So let me start by talking about Ax-Schanuel itself. Suppose you have n formal power series. You can talk about meromorphic functions, it doesn't really matter. There are q linearly independent modulo constants. So no q linear relation gives you a constant function. And you adjoin these n functions and they're n exponential. So you get a very similar setup to the classical Ax-Schanuel conjecture, excuse me. But now we're working over the complex numbers. So we only care about transcendence degree over C. Then the analog here is that its transcendence degree is at least n plus the rank of this Jacobian. Essentially, the idea for this plus is, before the idea was we could make one of alpha 1, alpha and e to the alpha algebraic. But now, if you adjoin a variable, not just a transcendental number, but an actual variable, x or f, then x and e to the x is pretty clearly, it adds a transcendence degree of 2, because formally speaking, the field C adjoin x and e to the x has transcendence degree 2. So for every variable you adjoin, you get this extra plus 1. Okay, so there's other ways to motivate this. In particular, it helps, and for generalizations, it becomes much easier if you think about this all geometrically. So let's just look at delta as the graph of the exponential function from C to C star. And now, given these formal power series Fs, let's think of them as giving us a analytic map from some base B into C to the n. So they parameterize some locus in C to the n, and we can think of G as the graph of this locus. So it's a map B to C star to the n cross C to the n. It really goes from B to delta. Then to rephrase this theorem here, this transcendence degree here is just a dimension of the Zariski closure of the image of G, because the Zariski closure dimensions care about transcendence degree. And this here, this rank, is just a dimension of the image of G as an analytic variety. And so this allows you to formulate the Ax-Schanuel theorem as an unlikely intersection. If you take an algebraic W in C star to the n cross C to the n, and you intersect it with this graph here, and you don't come from a subtorus, so nothing sort of special is going on, then the codimension of a component of the intersection equals the codimension you started life out with. Everything's expected. So if something is unexpected, then you must get some Q-linear relation, which amounts to this being contained in this graph of this coset of a subtorus. So, okay, you can formulate.
Can I ask something?
Yes, please.
But how do you make sense of that when it's just formal power series?
Yeah, sorry. So I skipped past that. Absolutely. To make sense of this, you need to imagine these are convergent power series. And then you can, using Seidenberg's embedding theorem, reduce to that case. But you're absolutely right. To make this actually make sense, these have to be convergent. Thank you. Okay, so then there's a lot of history of Ax proved the Ax-Schanuel theorem, and then it's been generalized to various setups. I just want to record some of them here. And there's been a lot of prior work on the Ax-Lindemann theorem due to people like Klingler and Umo and Yafev. So I can't list every name here, but in terms of just the full Ax-Schanuel theorem, there were versions proven by Shimura varieties and then variations of hard structure. Then recently, Kenneth Chu and Gao Klingler independently proved a version of this for variations of mixed hard structures. There was a recent work due to Blaske-Sanz, Casal, Freitag, and Naglu, which actually introduced a new method because they don't use definability or point counting. They have and they can cover some new cases. They work in the framework of essentially general principal bundles. And what I want to describe is this work with Ben about periods of geometric local systems. So this is just to sort of give you a sense of what's been done in the subject. And here is our ultimate version, which is a bit, now that I think about it, of a pretentious title. But the current version, which implies all the other ones that I've written down before. So I'm going to write it more generally, but the example to keep in mind is, again, the smooth projective family of y over x. So this version actually, the nice thing about it is you don't know anything about Hodge theory or Shimura varieties. You're just going to work with a local system on the base, which we're going to call V. And in the example, you can think of V as being the family of these nth cohomology groups. of the fibers. So the nth derived push forward of the complex numbers. But if that doesn't help, just think of an arbitrary local system V. So V is kind of a topological object. But then if you look at V and you tensor it with the field of the holomorphic sheaf of functions, basically, you get some vector bundle. Then it turns out by the Riemann-Hilbert correspondence, this vector bundle has a canonical algebraic structure. And a good example of this is you can think of, in this case, it amounts to the relative theorem cohomology. So this exactly gives you the setup we've been talking about in the case of a family. And then any local system V has some algebraic monodromy group because the fundamental group acts, and you can take Zariski closures. And then what you get is you get this multisection from the base to maps from the fiber of V at a fixed point to this V itself. So this itself is an algebraic vector bundle. And the natural multisection here is flat continuation. So essentially, if you're over a point little x, what is this map from the fiber at x naught to the fiber at x? It's you pick a path between them and you just take flat continuation from this one to this one. So essentially, it preserves the local system V. The reason it's a multisection is because you have monodromy. So if you pick a path, then you pick a different path where you go around the loop, so you're not homotopic, you will get a different element of this Hom group. And what are the coordinates of C, if you pick an appropriate basis here? Well, it's just changing bases from differential forms in this case to Betty cohomology. And so the coordinates of the C are exactly the periods corresponding to this family. So this structure here gives you a way to talk about periods for arbitrary local systems, where you don't need Hodge theory and you don't need varieties at all. And now you can look at delta in this case to be just the image of this multisection. And you can show elementarily that its Zariski closure is a G torsor over X. In fact, you can describe this explicitly. It's sort of all maps from Vx naught to V, which respect the G structure in both of these guys. I don't want to go into that, but it's a very familiar object. And so now we just modify the statement of the regular Ax-Schanuel to this setup, which formally is very similar. If you take something in this Zariski closure that's algebraic, and you intersect with this transcendental thing delta, then unless your projection is contained in something which has smaller monodromy, which is what weakly special means in this context, the codimension is what you expect it to be. This is an Ax-Schanuel for periods, and it essentially describes all, just like the Schanuel conjecture describes, or the Ax-Schanuel theorem describes all relations between the exponential function and algebra. This describes all possible relations between periods and algebra, where you're allowed to take inverse, basically any first order logic operation is allowed. And I think one nice thing about this is, again, it includes situations that aren't geometric. So for example, if you care about proving Ax-Schanuel or studying transcendence for Fuchsian groups that aren't arithmetic, that's included in the setup as well. Okay, and so it turns out, I have 5 minutes. It turns out that, so I'll say why Schanuel implies the Andre-Grothendieck period conjecture. In fact, they're essentially equivalent. They're equivalent up to this fact that you have local systems that don't come from geometry, and the Andre-Grothendieck period conjecture comes from geometry. So if you make the natural generalization of the Andre-Grothendieck period conjecture to just local systems, then they would be equivalent. And here's the proof of this. I'll sketch it out here. And the idea is you can translate, in this case, all the field theoretic information to geometry. So if you have this L between K and K hat, then you can take a model for L, this T, and you get a map from T to X. And the embedding of L and K hat gives you a section over some ball B in X, analytic section from B to Tn. That essentially gives you this embedding. You take a function, an element of L is a function on T, you can pull it back via S, and you get a germ on X. And given a motive, you get a variation V over T. a local system V over T. And now we can just translate everything to this setup. So we let U be the image under this multi-section of the image of the section, and W is the Zariski closure. So the dimension of W turns out to be this transcendence degree, which the Andre-Grothendieck period conjecture tells you about, because L is what you get by going to T, and the periods are what you get by taking this multi-section. So that's over C. Now, if you work over K, you add this dimension X here, because K over C transcendence degree is dimension X. Dimension X is the same as dimension U, because it's just a section here. And now you just apply Ax-Schanuel. This transcendence degree is the difference of dimension W and dimension U. And by the Ax-Schanuel conjecture that we just described, that's at least the dimension of this monodromy group. So, okay, I understand this is hard to follow in a lecture with so much notation, but hopefully I just want to give you a sense of how these two things are equivalent. And finally, I want to say that, so again, the proof is the least interesting part, which is why I didn't say much about it. I'm sorry about that for those who haven't seen this before. But essentially, you can either follow the recent method of Blaske-Sanz, Casal, Freytag, and Naglu, and you can choose sort of built on their work. They have this notion of sparsity, and he showed that every monodromy group of a mixed variation of hard structures is sparse, which allows one to apply their method. Or you can just use the O minimality and Peter Zylstarchenko sort of definable Chow framework that was used by everybody I mentioned before, including Chu in the mixed variations of hard structure setup. And you can sort of upgrade it to this periods framework. And the first proof, one advantage is there's no O minimality or point counting, so it's sort of a lower tech kind of method. So yeah, in fact, they're equivalent, except for local systems coming from geometry. So you can make the same conjecture for arbitrary local systems, and it seems very reasonable. We don't yet have it in that super general framework, though we think we can get it. But as a moment, it's still open for local systems that don't come from geometry. And yeah, this one implies all the other ones that are known. But again, I want to emphasize that it's not a new proof. It builds heavily on the methods that were done before. It's just generalization. Thank you so much for your attention. Yeah, I'll stop here.